In this video, I want to revisit ionization energy and see what happens when you take away more than one electron. In other words, what happens to the first ionization energy as opposed to the second ionization energy, third ionization energy, and so on. Let's take a look at magnesium. The magnesium atom has 12 protons and 12 electrons. If we were to remove the outermost electron from that atom, it would leave us with 12 protons and 11 electrons. And again, that outermost electron would be removed. That takes 737.6 kilojoules of energy to remove that outermost electron. What happens if we want to remove that second electron from magnesium? Now that second electron is coming out of a positive ion, something that has 12 protons and 11 electrons. And when we remove that outer electron, it's going to have 12 protons, 10 electrons. But it takes much more energy to remove that second electron than the first one. And that is because the first one, while coming out of a neutral atom, something that has 12 protons, 12 electrons, this one has 12 protons and 11 electrons. The greater charge of the positive to a lesser charge of the negative means those 11 electrons are going to be held more tightly than these 12 electrons, and that makes it harder to remove. The more positive the nucleus, the harder it is to remove the electrons because of the greater attraction on electrons. But now let's look what happens to the third electron. Here we had about a doubling of the amount of energy, but now we have a much, much greater increase in the amount of energy, and that is because that third electron is now coming from a core energy level. It's coming from the second energy level, and that makes it much, much harder to remove. Not only is the nucleus more positive compared to the number of electrons, but it's coming from a core energy level. Perhaps this is easier visualized with the Bohr model. Again, the first ionization energy is to remove one of these outer two electrons. The second one is to remove all these outer electrons, but remember these are in the third energy level. But the third electron has to come from the core energy level, and that makes it much harder to remove. In the quantum mechanical model, again, here are the first two electrons, but the third electron has to come from the core, making it much, much harder to remove. If we were to look at the aluminum atom, if they remove the first electron, leaving 2, that might take a certain amount of energy, let's just call it X. To remove another electron, so there's only 1 left, it might take twice as much. And to remove that last one, then it might take 3 times as much energy. But the fourth electron is going to come from the core, so that is going to be much, much greater than the 4 times that energy. Again, here's the first electron, here's the next 2 electrons, but the fourth electron has to come out of the core. It's going to require much, much more energy. So what I want you to see here is anytime we move from valence electrons, the outer electrons, to the core, it's going to require much more energy. So for sodium, the first ionization energy is quite small, but the second is much, much larger than that, again because the first electron is outer energy level, but the second electron is going to be core. For magnesium, we see the huge jump between the second and the third. Again, because the first two are valence electrons, the third is going to have to come out of the core second energy level. And for aluminum, we see the huge increase between the third and the fourth because the 3 are outer valence electrons, but the fourth is coming from the core. And that is the pattern that we see in ionization energy.